Okay. Alright. So, hari ini kita nak belajar tentang ni yang saya tak suka ni. Saya nak okay. So, we are talking about the sediment transport now, okay? So, if last week if last week you already introduced to the initiation of motion, okay? So now we are calculating, or we want to know how we can calculate or how we can determine the transport rate of the sediment yang moving. So initiation of motion is the time for the sediment to begin to move. Now it's time for the sediment to move. So if you look at into this slide, my picture here, a very beautiful picture here, this is something that is happening in the water columns. In the water columns, you have the river bed here, okay? And then in the water column, what you will see that has a close contact with the bed is, we call it as the bed load. Okay, so the bed load. So kalau you tengok dia punya arrow ni, this is the process of the bed load. Okay, it can jump, it can roll, and also it can slide. So because of the slope of the bed, right? So other than that, you also have the particle that is always suspended in the water column. Yang kecil ni, which makes your water turn to the yellowish color. It is what we call it as a suspended load, right? So what is the sediment load? So it is normally measured in terms of the sediment transport rate or also in terms of the sediment discharge. So kita boleh panggil dia sebagai sediment transport, or also we can call it as the sediment discharge. Kita ada river discharge. So river discharge normally is the clear water or fresh water. But sediment discharge is the discharge of the particle with the water, fresh water. So the sediment discharge or the sediment transport rate can be measured either by unit Newton per second, by weight, it can be measured by weight in a unit Newton per second, or by mass in a unit kilogram per second, or by a volume in a unit of meter cubic per second. So in terms of per unit weight, we can say that our sediment discharge can be in a kilogram per second per unit weight. So per unit meter weight, or by the volume meter cubic per second per meter. Okay, so this one is by unit weight, and this one is by the volumetric unit. So in practice, we normally refer the sediment transport per unit weight. So per unit weight, it's either measured by the mass or it is just measured by the volume. So kalau kita kata kita nak kira kan sediment transport tu for our width of the river 20 meter, kita tak kira 20 meter, we call it per meter. So kalau you nak tahu keseluruhan or the what is the sediment transport rate for the river width of 20 meter or 30 meter, then you multiply lah by the width, then you will get the kilogram per second only. Okay, but normally in practice, we calculate the discharge, sediment discharge per unit meter width. So it is comprised of the bed loads and also a suspended load. Okay, so if you combine these two, bed load and suspended load, you will have a total load, right? So ini adalah mechanisms of the bed load transport. Ni selalunya kita will, what we consider is anything that is moving within this, what we call it bed load height. Okay, bed load height, which is sometimes they use A as terms, or we can also use any other terms lah. So this bed load height. So if you refer to any textbooks, or if we want to do a further reading on the velocity distribution profile, on the velocity distribution profile, you will actually see that your velocity distribution profile is actually divided by several layer. So it is only not one layer. Kalau yang you expose in undergraduate level, kita selalu cakap our profile is, velocity profile is always looks like this lah. But actually, if you go to any books of hydraulics or fluid mechanics, so actually this velocity profile is divided into 3 layers. So kita ada outer layer, kita ada overlap layer, and then yang bawah sekali ni, which is your bed load punya height ni, we call it a viscous wall layer. Viscous wall layer. And this is where your law of wall punya theory derived based on this 3 layer. So what I want to say here is that our bed load transport ni, dia actually moving in this viscous wall layer only. Why? Because of the because the turbulence, the turbulence happens above this viscous layer. Okay, so turbulence happen because of this occurs within this overlap layer or up to the outer layer lah. So because the turbulence energy cannot counterbalance the gravity and the intergranular forces, which is the gravity of your particle, your weight of the particle, and also other forces lah. Let's say last week we have been learn about the drag force lah, lift force lah, dan sebagainya. So that is why the particle is always settles at the bottoms of the bed. Okay, so dia punya the weight of the particles itself, which is governed by the gravity, pull the sediments or pull the granular or grain size on the bed. So that is why your bed load is always within this viscous wall layer. Okay, but because you have the additions of something, you are the power, because your river to it comes with the energy. Where is the energy come from? It's come from the river discharge, for example, the Q. So that is why your particle ni dia tak always, it is not always stay at one point. So it's moving. It's moving. So it's moving either by rolling, by sliding, or also by jumping along the bed. Okay, kalau dia roll tu macam you bergolek tu lah, macam dalam cerita Hindustan tu. Yang you bergolek tu, itu rolling lah. Sliding ni means that kalau you punya you have more, what they call it, you are the slope. You are the slope. You have a greater bed slope, for example, and then your particle tu dia slide. Okay, kalau jumping tu dia melompat macam ni. It is also jump from one point to another point. So Einstein theory of the bed load proved that this particle is actually not only rolling and sliding, but also they also jumping in one point to another point. And he say that also the jumping distance is about 100 times the 100 times the diameter of the particles. So every 100 meter, then they jump. Okay, that is what theory says lah about this bad load. Now the suspended load ni pula, so the one that is moving in the suspension. Nanti kita tengok lah macam mana dia moving in suspension. So because of this turbulent effects, and because of the upward components of the turbulent velocity. So you ada because dekat dalam apa tu water column tu nanti kan, and this is your bed, so your particle will always be stays in this region lah, above the viscous layer because of this turbulent effect. So velocity plays important roles in this process of the suspensions of the sediments, and that is because of the weight of the particle is less, so it cannot or it doesn't have the force. The gravitational force also is less, because of the weight of the particle is less. So that's why, and because of the turbulent velocity is high in the middle of the water columns. So that is why your particle is always in the suspension mode. Okay. So the total load is the combination between the bed load and also the suspended load. So kalau you ada equation, calculate for the bed load, and you have the equation to calculate for the suspended load, you add these two equations, you will get the total loads of your sediment in a river per unit meter width, for example. Okay, so that is the case if you have a separation between the bed load and also the suspended load. There are also theories that simplify the equation by not taking into account this bed load and suspended load, tapi dia dah generalize the equation to become one equation to compute this total sediment load. Okay. So for the bed load transport rate, kita ada I think 4 approach that we are going to go one by one. Which is one is the shear stress approach. Kita ada shear stress approach. And then we also have the energy approach, energy slope approach. We also have the discharge approach. And also last but not least is our velocity approach. Okay. So for the shear stress approach, kita ada several formula, right? So Du Bois in 1879 proposed that the bed load transport, which is a QB, is a function of this shear stress. And what he says, so Du Bois ni adalah orang yang pertama sekali yang explore the sediment transport punya equations. The sediment transport punya equations. So what Du Bois do or assume in his equation is that he assumed that the sediment particles move in a layer along the bed, and this layer move because of the tractive force or the shear force that acting along the bed. So minggu lepas I have shown you that kalau kita ada water columns, okay, and then you ada granular particles kan. So on the bed you ada also your shear stress. Shear stress that is acting along the bed. Okay, for the sediment to just move, then your P node must be equals to your PC, which is your critical shear stress, where you can use the shear parameter to calculate your critical shear stress. Okay. Apa yang dimaksudkan dengan the several layers tu? Okay. So ini yang dimaksudkan dengan the several layers of the Du Bois. Okay. So the top layer ni, Okay, yang ni kita panggil the top layer, and yang bawah sekali adalah the lowest layer. So the top layer ni is always transported with a very high velocity, but yang the lowest layer ni when the velocity is equals to zero lah, dia kata. So the movement of the velocity ni, dia kata increase linearly from the top to the from the bottom to the top. So from the zero to the maximums of the velocity. Okay, so what we would like to investigate is actually the one that is at the bottom lah, because that is the maximum one, the condition when the incipient motion takes place. Okay, so Du Bois punya equations ni dia okay, so the attractive force is determined by the shear stress equals to this apa ni kita panggil ni? Lupa dah saya. Omega, bukan omega, apa kita panggil? Iskandar, apa kita panggil ni Iskandar?
Gamma.
Oh, gamma. Okay. So gamma multiplied by the depth of water, multiplied by this slope, the bed slope. And under the equilibrium conditions, then this active force should be balanced lah by the total resistant force between this layer. So they can balance between the layer, and that's come out with this equation, which is the CF times the M. M is the numbers of layer. E is this interval of each layer, and multiplied by this unit weight of the sediments. Okay, so they say that if the velocity varies linearly between first layer, where the velocity is zero, and also this M layer, which is the maximum layers on the bed. So he said that the bed load transport QB, which is equals to this eta times the average of the velocity v squared over 2 multiplied by these layers. Okay. So because we are only interested on this top of the sediment, on the surface of the bed, which give you the maximum conditions of the flow, okay, and we will say that at the incipient motions, then our M is always equals to 1. So for the M equals to 1, so means that your tau naught is equals to your tau TC. So this one is your back shear stress, back shear stress, and this one is your critical shear stress. So if you input these conditions into these equations as derived by the Du Bois, so what you will have here is these equations. Okay, now your QB is a function of your shear stress. Okay, it's a function of your shear stress. So if you look at here is your back shear stress, and here is your critical shear stress. So you have to make sure that your back shear stress is always greater than your critical shear stress in order for the sediment to move. So what is in this colored box here is actually the parameters that is related to the sediment properties. Okay, so we can say that our QB is equals to the K, which is the sediment parameters here, times the tau minus the tau C. Okay, which is given in this equation. So now K, which is the one that derived before, is actually need to be evaluated because it depends on the sediment characteristic as I mentioned. So one way that we can solve this K problem is we can use the Stroop 1935 by calculating the K equals to 0.173 divided by the D power of 3 over 4. So now D here is your sediment size. Okay, so your sediment size. So if it is not given to you, what is the size of the sediment, then we normally take it as a D50, okay, as our sediment size in this equation. But this equation, so if you put this equation K into this Du Bois formula, so what you will have is this final forms of the back load transport derived by the Du Bois, but this is in a unit feet cubic per square per second per meter. So this is in a British unit. So if you want to use it in a SI unit, so then you have to, or they have made some of derivation or multiplication factor to multiply with some multiplication factor, so that you will get 6.89 times 10 power negative 6 constants. If you want to use the equations in SI units, meter cubic per second per meter, right? Okay. So this is the relationship between the back shear stress, tau C, and also the sediment size on your y-axis, right? And then you also have the K constants, K constant, which is in that you can you also can use this graph to determine what is the K value, the K values. So yang K ni dia kat sini lah. So you hit one of this line, your your critical shear stress and your particle diameter, okay, and then hit this K line and then go straight to the right, and you will find what is the K value, the K value, and then you can input it into this Du Bois equation. So the difference between this graph and this graph is in the unit sajalah. So this one is in the British units, yang atas ni, and the bawah ni is in a SI unit, in the SI unit. Okay. So this is the graph that was derived to determine the K value for the Du Bois sediment transport equations. Okay. But the limitations of this Du Bois transport equation is that because this equation is derived based on the small scale laboratory flow, okay. So dia punya, it is questionable whether this equation can be used to calculate the sediment discharge in the real river or not. Okay, in the real river or not, because of this sediment size. Also, the range of the sediment size is also limited. Okay, so you can use Du Bois to calculate the back load transport as a function of the shear stress. So the second formula that you can use to calculate the back load transport, which is still under this shear stress approach, which is the Scheele formula. Okay, so the Scheele formula give you these equations of your back load transport, which is here where the shear stress approach take into consideration. Okay, so in this case, you add the extra parameter, which is this water discharge, Q. So, and Q here is the water discharge per unit with channel. So it is small q. Small q, bukan yang big q tu. Kalau big q dia dah memang meter cubic per second. So this one is meter cubic per second per meter. Or would say that meter squared per meter lah. Your sediment discharge. So in order to use this shear parameter, then you must know, or you must determine what is the water discharge or the flow discharge in the river. Okay. Similar also to the buoy. Then in order for the sediment to move, then your back shear stress tau must always be greater than your critical shear stress, the tau C. Okay, and you can use this formula, which is the dimensionless of your shear stress that is always greater than 0.057 if it is at the critical conditions. You jangan pakai Meyer pula. So because this is a shield formula, then you have to use the shield incipient motion criteria. Okay, unless if it is stated, then you can use the others formula lah, like near Peter, or we can use the apa yang kita belajar last week. Saya tak ingat dah. Apa Khairina yang kita belajar last week on the incipient motion tu? What are the other critical shear stress that we can use other than the shear? Ingat tak?
Center.
You can use also the center. Yeah, you can also use the centered method using the graph kan yang bersimpan CO tu. Right? So just use this formula to calculate. So D here is the sediment size. So similar, kalau dia tak bagi tahu apa-apa, then you have to use that D is equals to your D50 lah. G is your gravity, rho is your density of the water, and rho s is your density of the sediment. Okay, so just plug in the values that you have, and then you will get the QB, or the bed load transport rate in volumetric method, which is in meter cubic per second per meter. Okay. All right. So other bed load formula is by the Kalinsky in 1947. So Kalinsky kata the movement of the bed load transport is not always steady. So macam yang Du Bois and sediment shield tu, dia kata the movement of the sediment transport in the river or on the bed is steady. But Kalinsky argued that because he said that he assumed that the velocity of the sediments grains of moving in the bed is actually given by these equations. So it's something that has to do with this turbulent velocity functions or turbulent flow theory lah. I would say a turbulent flow theory. So US here is the average sediment, the average or mean sediment. B here is the constant. So a coefficient that is normally taken as a 1 or close to 1. And then you have the U, instantaneous transport, and then you have the BC, which is your critical velocity of the parameter. So if you applying the turbulent flow velocity, which is here, so he said that the turbulent flow velocity theory, which is the average velocity divided by the shear velocity, is a functions of this shear stress, functions of this shear stress. So kalau you put these equations, sorry.
The B tadi apa doktor?
B ni adalah constant. Dia constant. So normally that they close to 1. Close to 1 lah. Okay. Apa ni? Okay. So this one is the applying the turbulent flow velocity. Okay. All right. So what Kalinski do is that here propose this way to calculate this sediment transport. The QB is this backload transport. It's equals to the alpha times the P times the D times this average velocity. Okay. So alpha ni adalah dia punya shape factor. It's a shape factor which is depending on the size of the or shape of the particles. Right? Normally, kalau we take a uniform shape, which is a sphere, then the value of this constant is 2/3 lah, something like that. Okay, and then P here is the fractions of the bed that is covered by the particles. So dia ada layer, a layer of particles that is covered by this particle lah. So if you applying the flow turbulent flow theory in these equations and do the generalizations where the constants are like the alpha and fraction of the sediment can be removed out. So it simplifies that your QB now is functions of this tau C over tau naught multiplied by shear velocity times the diameter of the particles. Okay, d50. So for the Kalinski itself, dia pakai his own equations to calculate this critical shear stress. Okay, which is equals to 0.12 multiplied by this submerged weight of the particles, specific weight of the particles, and multiplied by the size of the particle, d50. Okay, and you can also use this graph of the Kalinski to determine what is the value of your backloads. But on your x-axis, you are the equation for this Q divided by U star times d50. Okay, and the y-axis here is this ratio of your tau C over tau naught. Okay, so once you calculate your tau C, so your tau C you calculate using this telephone equation as 0.12 multiplied by this S gamma S times d50. Okay, and then your normal back shear stress you can calculate using this rho G Y S naught. Okay, so once you get these two equation, hit one of this, hit this line, and go down. Then you can get the constants for this Q over U star over times d50. Okay, so U star you can use the equations that we have learned last week or last week, I don't remember, which is equals to the square root of GR SON. Okay, and then d50 is the diameter of the particle. Then you can get the value of your sediment transport in apa ni, saya dah lupa dah. Wait, Kalinski is in a unit of volumetric. So it is in the meter cubic. So this one is in the meter cubic per second per meter. Okay. And then further, we have this, last but not least, Chang, Simon and Richardson in 1967, which he developed or they developed this equation based on these data from the Colorado rivers, Colorado's rivers case study. So he developed what they call it this semi-empirical formula, which is based on this shear stress juga, based on the shear stress. So what you can see here is that the direct empirical formula that you can use to calculate the bed load transport, okay, which is equals to the KB times this submerged weight of the specific weight of the sediments, and then you also have the tangent alpha here, which is the your alpha is equals to these angles of ripples, which is depending on this sediment size, and you add also the mean velocity, So similar to the shear and Du Bois, you also have this shear stress, your shear stress that should be multiplied by the velocity to calculate or to determine the QBW. Okay, and we simplify this key, or they simplify these terms, KB times all this with the KT. Okay. Which is your KT is equals to this stuff lah. To this stuff. Okay. So kalau you nak dapat the specific weight of the sediment ni, then it must be the specific weight of the sediment minus the specific weight of the water, then you get the specific weight prime, or the effective specific weight of your sediment. To get this apa ni KT value here in this equation, so you can use this Chang and Simon and Richardson graph, which is on the x-axis is the parameters that related to your shear velocities, and also this shear stress. S here is this slope of the river, and then DE is this diameter of the particles, and you have a different lines of your D, of your particle size in this graph. So if your D is given in the equations, then you can determine what is the KT value, right? Use that value and then plug into these equations to get this bed load transport in unit pound per second per feet. So this is by weight. This is by weight. Okay, so kita dah ada 4 ways or approach that we can use to calculate this bed load transport. So one is Du Bois, second one is the shear, third one is the Kalinski, and the fourth one is the Simon and the gang, Simon and Richardson. Simon, Chang and Richardson. So kalau you tengok all these equation, semuanya ada related to this shear stress, which is your tau minus the tau c, the difference. So be careful also with the unit used in those equations, because some equation applies the sediment transport by weight, some equation use the sediment transport by volume. But both units are acceptable in calculating the bed load transport. The next approach is the energy approach. Okay, so untuk energy approach ni, dia ada dua equation saja, which is by this Meyer-Peter approach, and another one is Meyer-Peter-Muller equations. Or equation ni equations ni sebenarnya. Okay. So the first thing that Meyer-Peter did is that dia buat experiment in a large flue, okay, and then dia pakai water discharge in that equation that can be varied up to 5 meter cubics per second, and then dia juga pakai sediment discharge that it ups to 4.3 kilogram per second meter, and then from the experiment, he come out with this relationship, with the relationship. So in this case, your D is equal to the D50 always. But if the question asks you that the particle is a mixture of the non-uniform particle, then D must be replaced by the D50. Okay? S here is your bed slope, it's your bed slope. Tapi the drawback of this equation, of this first equation developed by the Peter Meyer, is that it is only applicable for the gravel material. So for the coarse material, which is greater than 3 millimeter only, right? So where is this sediment transport in these equations? So the sediment transport rate that you want to calculate here is actually this one. So the QBW power of 2 over 3, and this Meyer-Peter equation use this sediment transport by unit weight. Okay, by unit weight. Okay, so dia kata this equation is not applicable to the natural streams or natural river, because it's only take into account this material that is greater than the 3 millimeter, which is not commonly found in most of the natural river. So what he did next is he came out with these quite long equations, which he named it as this Meyer, Peter, and Muller. So Meyer, Peter, Muller equations in 1948. Okay. So dekat mana pula you punya sediment transport rate dekat dalam equation ni? So kalau you look at on the right side of the equations, so we actually want to determine what is this QBD, or the sediment transport rate in meter cubic per second per meter. So dekat mana dia punya energy approach dia dekat sini? So SF here is your energy slope. Okay, is your energy slope. So I think in our or in your hydraulic class or in your fluid mechanics class, you know how to determine the energy slope. Still remember how you calculate the energy slope from the previous course. Safwan, masih ingat lagi tak?
Wait kan.
Hmm?
Sekejap, saya Google.
Ada bayang-bayang pun.
What is energy slope? Energy which represent the rate.
Ah.
Energy gradient.
Energy gradient. Tu aja. So kalau kita ada apa tu macam profile like this kan. So you have the datum and then you have the depth 1 and then you have the depth 2 kan. So you ada apa tu you ada energy red line. Mesti ingat ni. Okay. So above this water surface profile, you ada kalau you ada Y1, you must have your P1 squared over 2G kan. And then downstreams of the river, you ada Y2 and this one will give you the P2 squared over 2G. So we have learned from the specific energy that our E is equals to Y plus B squared over 2G. So this is the specific energy equations. So kalau you ada a distance of this, let's say a river with a L distance, then you can calculate the SF energy or the energy slope, which is equals to your E1 minus E2 divided by L. Masih ingat lagi this diagram?
Hasil.
So this is a very famous diagram to calculate the energy slope. Okay. And then here, if you look at this Miller-Peter-Muller equation, you ada D. What is this? These terms. AB. What is this term represent?
Forgot, doctor. Forgot.
Forgot. That you say that. Mano?
Yes, doctor.
So what is this term represent for in this Miller-Peter-Muller equation?
I think the shear stress.
Yes, that is the critical shear stress terms for the Miller-Peter-Muller. Good. Very good. All right. And then on the other side of the equation, you add also this constant, which is this is what we call it a roughness, something that related to the roughness equations. And to determine the value of the K, you can use this Strickler roughness equations. Strickler roughness equation, which is give you this velocity divided by this R. H here is your hydraulic radius multiplied by the slope, by the slope of the bed slope. And then the K prime here is also the roughness that is related to the bed form. Okay, roughness kita ni dia ada banyak tau. And the one that you only calculate is the average or general roughness. So roughness kita ada banyak. Okay, so if I say that R is our roughness, so then our R is actually divided by 2, which is R prime plus R double prime. Nah, ini kalau you dalam fluid mechanics class you tak belajar ni, R prime dengan R double prime ni. Okay, so what is the R prime and what is this R double prime ni? So the R prime ni is actually the roughness that is related to the bed form, or related to your bed, the formation of the bed. So bed kita ni is not only always horizontal bed. Bukan plain bed saja, bukan rata. So dia ada bentuk. It has a different shape of the bed. Next part nanti you will be introduced what are these different types of the bed form. Okay, so for that different bed form, you pun ada dia punya roughness itself. So in this equation, kita pakai K lah, K prime. And another one is the roughness that is related to the grain. The particle size itself has its own roughness. Has its own roughness. So if you combine this grain particle, the roughness for the grain and the roughness that is due to the bed form, what you will have is your general roughness, or your generalized roughness, a roughness that is related to the sediment and also to the bed in the river. Okay, so you can use these equations to calculate this K prime, and see that now instead of using the D50 as your sediment size, so to calculate the K prime, that you have to use the 90% of the particle that is passing the sieve, which is your D90. Okay, your D90. Right. So Zeller in 1963 they simplified. And they reported that actually the K over the K prime, which is this Strickler roughness, and also the roughness that is due to the bed form, is actually between 0.5 and also 1. Okay, so dia buat eksperimen, dia dapat tahu the ratio of this roughness is actually between 0.5 and also 1. So dia kata kalau dia punya K over K prime is equals to 1, then there will be no bed form. Okay, so tak ada bed form. Bukan tak ada bed form sebenarnya. Dia ada bed form, tapi the bed form is actually the bed is not bukan influence. They will say that no formation lah of those various bed form. So dia macam plain bed saja. Okay, dia macam plain bed and horizontal bed. Dia tanah rata saja. So would say that kalau dia tak ada bed form, then the K value will become, or the roughness value in these equations will directly become 1. Okay, but if the K over K prime is equals to 0.5, then that indicates your bed or your river bed too, it is not plain, but it has a bed form. Okay, dia ada bentuk bed form. Okay, so you either created a ripples, ripples ni dia macam bentuk macam ni, or you created a dune, undulated or sinusoidal profiles of the beds on your river bed. So itu maksudnya a strong bed form. You ada bentuk tu. Kalau tak ada bed form tu maksudnya your bed tu dia horizontal sajalah. Dia horizontal, no changes on the bed. Okay, so this is the two equations that you can use to calculate the sediment discharge when the energy slope take into considerations. Okay, the third one is this water discharge approach. Water discharge approach ni dia ada banyak juga sebenarnya, but I think kita tengok on the simplest sajalah. The simplest one, which is in this case is this Scottish approach. Okay. Scottish approach, which is directly give you these equations equals to the 2500 multiplied by the slope. This is bed slope, dia bukan energy slope. The bed slope, power of 3/2 multiplied by this water discharge. Yeah? So water discharge approach, so or we call it access water discharge approach. So in this case also for the sediment to move, so for the sediment to move along the bed, then the Q, which is your normal discharge or the average discharge, must be greater than your critical discharge. Okay, so for the critical discharge to allow the sediment to move. So Scottish also use these equations to determine the critical sediment discharge. Okay, very direct solutions multiplied by this factor, unit weight of the sediments, and then you have this diameter of the particles, and then you also have this slope of your river. And to calculate these equations, the unit is by unit weight. The unit is by unit weight, so it is in kilogram per second per unit width of the river. The next one, or last but not least, is your velocity approach. Okay, so we can use the Nielsen in 1992 to calculate this velocity approach. Stress in a volumetric unit. So it is a meter cubic per second per meter. So kalau you perasan in my slide tu, sometimes I use the QBV, sometimes I use QBW. So this is by volume. So this is by volume, and this is by weight. Itu saja beza dia. So by volume is this one is meter cubic per second per meter, and this one is kilogram per second per meter. Okay, so because they are different approach ni, dia pakai the final form equation is depending on units lah yang dia orang investigate. So that's why you have the different units for different bed load transport rate. So for the velocity approach, it is a very direct solution here. But actually, I was argued why they call it this velocity approach, because there is no functions of velocity in these equations. But what I see here is actually related to the bed shear stress, and also, yeah, this is also the bed shear stress. So this tau and also this tau is similar. It's a similar, but maybe there are something like I don't know. I couldn't find the full descriptions of this Nielsen. Why they call it as a velocity approach, while in the final form equations there is only the presence of this shear stress. Shear stress in approach, shear stressor. So I would say that also this Nielsen 1992 is fall under this shear stress approach. But if I say that it is fall under the shear stress approach, there is no terms that related to this tau c. Okay, so something that something is missing. I don't know, but I believe that along the way, this equation is derived. There must be some sort like introductions to the velocity approach that has been used by Nelson before he came out with this final form equation. But don't worry too much about that. We are not going to learn the history of the equation. But what we interested here is that we have the equations of the Nelsons given by these expressions, and we can determine what is the volumetric method, volumetric sediment discharge that transport in the river. So in this case, D here is your sediment size. So as usual, if it is not given the size, then you take D as your D50. D is your It's your D50, and then tau here is your shear stress, your bad shear stress and normal shear stress, which can be calculated by the rho times G times R times also the S. Okay, so that's all for the bad load transport example. Okay, sorry, for the bad load transport equations, right? So what I want you to do is try to do this example. Okay, you are given the conditions of this river. You are given the aperture. So the energy slope is given, the bed slope is given, discharge per unit width is given, the Manning roughness is given, the viscosity of fluid is given, the hydraulic radius is given, and also the energy slope also. This is SF. It is given, okay, and the sediment properties also given as 0.5 millimeter for the D50, right? So just plug in all this value in those equations, and then you will get the bad load transport rate. So for the bad load transport rate. Okay, so mungkin kita boleh buat satu code dulu, and then the rest you can continue at home. Okay, so maybe we can do it for the shell, right? So for the shell parameters, the equation is the QB is equals to this QBV, volumetric method, is 10 times Q times S naught times rho squared with kg. So shell use the shear stress approach. Yeah? So the shear stress approach here, what you need to do is that your Q is given here, 3. Yeah? Your Q is given 3, and then you are the S naught also given here, 0.0004. Okay, and the rho is the density of the water. So the density of the water is 1,000 kilogram per cubic meter. Okay. And then you are the sediment density, which is given here, 2,650 kilogram per meter cubic. So G is your gravity, which is 9.81 meter per second squared, right? And D here is the diameter of your size particle, which is equals to 0.5 millimeter. Okay, so what you need to find here is your tau, which is equals to the rho G R S naught. Okay. So the hydraulic radius is given here. So you can use this as a 5. Sorry. Yeah, it is correct. So 0.15. The slope is 0.0004. This one is 1000. This one is 9.81. And then you will get the value lah in Newton per meter squared. All right. And then you need to use the shield diagram. So in order to use the shield diagram, you have to determine what is your shear velocity dulu. So shear velocity is equals to this shear stress divided by rho water. Then you get one value of your shear stress. And then you need to also determine your Reynolds number, which is equals to the shear stress multiplied by this D50 sediment size divided by kinematic viscosity. Okay, you get the one value. Then use the shield diagram to determine what is your tau C. Shield. So the tau C is equals to this rho.
Dia macam laju sangat.
Laju.
Doktor yang Reynolds number tu formula dia dekat mana ni?
Dekat slide yang depan, slide initiation of motion yang shield tu. Not here, not in this slide. Previous class punya slide.
Oh. Okay. Previous class eh?
Previous class punya slide. So yang ni yang previous class punya slide. You start, tau, Reynolds ni, semua use previous class punya slide. Okay. So once you get the tau C, then you just put it into this value lah. So you dah ada tau, you dah ada tau C, and then you can plug in the value, and then you will get the answer. Very easy and straightforward also. So my advice is that you tengok dia punya equation tu for each of the equations given to you, and see in each equation what are the parameters required. So kalau dia nak minta tau shear stress, you carilah equation untuk tau tu macam mana. Kalau you nak cari tau C, okay, then you go back to this either shear or center or millimeter untuk determine dia punya critical back shear stress. So kalau near amphitheater mula tu, dia request you to find the Strickler roughness K, and also the K prime roughness that is due to the sediment, bed form. Sebab dia tak bagi tahu dia, dalam question ni it doesn't give you whether the bed has no bed form ke, ada strong bed form ke. Then you have to fully utilize the equations that given to determine the K and also the K prime for near amphitheater molar equations. Kalau dia bagi tahu senang lah. Tak payah calculate lah. You just can take. It's either 1 or it is 0.5. Okay. And then tengok kalau dia equation 2 require you to find the slope. Energy slope, for example, if it is not given to you in the equations, then you kena faham lah the equations tu. Dia mesti ada the flow that is coming from the situation where the flow comes from the downstream with one depth to a flow that is going to the downstreams of the river with a different depth. So dari situ baru you boleh dapat dia punya energy slope tu lah. How are you going to calculate it? Okay. And then velocity, semua tu then you have to check. Okay, so maybe next week kita boleh tengok lah how you solve the equations. Okay, kah? Sekarang dah pukul berapa? Huh?
11:30.
11:30. You all masih boleh digest lagi ke ni? Aku value. Okay, so now let us move to the more complicated equations. Yang tadi tu dia tak complicated sangat, dia biasa-biasa je. So this one is more complicated. So you do it for the shield meter, Peter. Nanti kat rumah you buat lah. You will get this slide later on, and then kita tengoklah nanti next week we will discuss on how you solving this problem. Alright. So sediment transport. Next mode is the suspended load. Okay. So macam saya bagi tahu tadi awal-awal, the suspended load ni dia always suspend lah, always in the suspension mode. Dia terbang or dia berada above the viscous layer, above the viscous layer. So the main mechanisms of this suspended load ni dia is because of the turbulent velocity, because of the turbulence. So dia that's why dia terapung. So kalau you tengok on this our river, so our river in Malaysia ni dia most of it is actually banyaknya suspended particle. Kalau you tengok the river tu, dia very clear river, which you can see the water clearly, the bed, the gravels or apa-apa yang berada dekat atas air on the bed lah. And then you will say that the river is actually dominated by this bed load. So but normally overall, commonly bed load punya transport ni, it takes about 25% of the total load transport. So maksudnya 25% daripada sediment load in the river ni is dominated by the bed load transport. So the other 75% tu lagi adalah sebenarnya the suspended load. Okay, the suspended load. So if you have a further increase in the shear stress, on the back that cause some of the particles to be carried out into the main flow, and it is lost contact with the bed. Dia dah tak ada contact lagi dengan bed. So then, and if this particle travel with the velocity that is equals to the flow velocity, and this is what we call it as the suspended loop. Okay, so dia terapung-apung in the water column, and we can use, or normally, the suspended load is given by this definition, which is the integrations from the depth of D to from depth of A to D. D itu is your water column, or your water depth, sorry. A two is this bed load layer, or your thickness of the bed load, the thickness of the bed load. So dekat atas bed tu you ada berapa apa ni sedimen ataupun bed load sedimen lah yang mengendap. So and it has its own thickness layer. So kalau you take that profile from the bed load layer up to the water surface, and then you have this average velocity of u, you multiply by the c. So what is the u and what is the c? So u is this average velocity, time average velocity, and then c ni is this concentrations of your sediment, the concentrations by the volume lah at a distant y. Okay. So this is the schematic diagrams of actually what is really happening in the river. So kalau you ada depth D ni, saya kata, so maksudnya dekat bawah ni dia ada satu lagi layer, which is, this is what we call it as a bed load layer. So kalau you take the integrations between this bed load layer up to the water surface, D, then you ada your velocity distribution profile, which is like this diagram. You multiply by the sediment concentration, okay? So C, and then what you have here is your suspended load. So kalau you tengok your suspended load ni, dia actually banyak rapung lah in the water column. Okay, so this is your mechanisms of this sediment transport. So the suspended load ni, it is dependent, your QSS ni is dependent on this shear stress, is dependence on the fall velocity, and also its dependence on these systems. This eta. This one is actually the AD diffusions. AD diffusion terms. Okay. So AD diffusion term ni macam kalau you kentut tau. You kentut, and then your punya kawan that stays, let's say 2 meter from you, will smell the kentut. That is the effect of the AD. Itulah maksud dia. So dalam sediment transport pun macam tu juga. So there is the effect of this AD, which is also the concentrations of the sediment is dependent on this. So kalau you tengok the books of Cik Tek Yang yang saya bagi tahu minggu lepas tu, the mechanisms of the sediment transport. Siapa yang dah download buku ni? Ada jumpa? So dalam buku ni dia ada bagi tahu the detailed explanation lah on the mechanism of the suspended transport, which is based on the what they call it the exchange theory of equilibrium conditions. So the exchange theory of equilibrium condition. So dia kata dekat dalam river kita ni, so dia ada dua proses, which is that make the sediment stays in suspension lah. One of the process is this the downward flow of the sediment, downward flux of the sediments, and also the upward flux of the sediment. The upward flux of the sediment. So apa benda lah downward flux dengan upward flux ni? Okay. So the downward flux means that it is something that related to the concentrations and also the fall velocity. Okay. Berapa banyak dia punya berapa berat the particles, I mean that how heavy is the particles to be or to move in the downward motions. Berapa banyak dia nak yang boleh dia jatuh lah maksudnya. Yang boleh dia jatuh. Okay. Kalau kita ada this imaginary layer lah maksudnya. So you punya particle tu ada dekat sini lah contohnya kan. So dia berada dekat sini dan dia ada berapa berat dia boleh stay. Kalau dia berat maksudnya dia jatuh lah. Kalau dia tak berat, which is your fall velocity is also smaller or greater than your normal average velocity, then dia maksudnya dia stay in suspension. Then another one that makes the particles stays is this upward flux. So upward flux ni apa pula? The upward flux ni is this something that is related to this eddy diffusivity. So kita ada negative eddy diffusivity multiplied by the concentrations over the depth Z. Over the depth Z. So kenapa kita panggil Z? Because Z tu maksudnya dia particles that at a certain point in the water column. Dia boleh berada di sini, dia boleh berada di sini, so dia boleh berada di sini. So along this depth B, but with the variations of Z, elevations of Z. So dia ada dua ni lah. So these two process, the downward flow and also the upward flow. So kalau you go detail into the derivations of this upward flow and the downward flow, what you will have is that you will have this, or you will come up with what we call it as a Rose equations. So panjang-panjang yang aku cerita tadi tu adalah dia punya mechanism sajalah. Okay, but the final form of the sediment transport punya concentrations, equations is given by this Rose equation. So ini semuanya kerja Rose, dia yang develop this equation. So what you have to find here is that, what you will get here is that the C is the concentrations by weight at a distance y, so along the water columns, and then CA is the concentrations above the bed, so ataupun dekat dia punya bed load layer. Okay, concentration at the bed load layer is equals to the D. D here is the water depth, your river depth, and then Y here is your apa ya Y? The positions or your depth of your particles tu. So dia pakai Y dekat sini. And then from the equilibrium theory yang tadi tu, downward and upward flux tu, so they come out with this Z parameter, which is Z parameter ni is what we call it as this Rosse parameter, okay, which is equals to the fall velocity divided by the von Karman constant. Jangan tanya saya apa ni von Karman constant, aku pun tak ingat dan tak nak ambil tahu kenapa dia jadi von Karman constant, which is always equals to 0.4, and then multiply by this shear velocity. Multiply by this shear velocity. So kalau you tengok dia punya ni, this is where the downward components, the downward components of your particles to take place. So this is the conditions, or you can use these equations if you have fine particles. When your beta is equals to 1. When your beta is equals to 1. So kalau you ada coarser particles, then you have to use this equation, which is similar to the first one, but with this rows or with the parameters of Z1. So Z1 is equals to the Z divided by the beta lah. So kalau the beta is equals to 1, then Z1 is equals to Z. But if the beta is lesser than 1, then you have to use this graph. Okay. So kalau you plot these equations, or you further utilize these equations, then you can come out with these diagrams.
Excuse
So
me,
this is what
doctor.
we call it. Yes.
Doctor, the D is water depth and the Y is the particle depth, is it?
Yeah. D is your water depth. Yeah, correct. So from the surface to the bottom lah. So this is your D. So Y is somewhere because our particle is not on the back end, it's suspend.
Yeah.
So most probably maybe at the middle of the water column. So this one could be your Y lah.
Y is from bottom.
Yes, from bottom.
Alright. Thank
Yeah.
you.
All right. Okay, so then that equation also can be translated into this graph. Okay, so ini yang dia punya concentration profile. So what you see here is your concentration part. Okay, so yang dalam lengkuk ni, or the curve here is the value of the Z. The value of the Z, yang you ada power of Z tu kan. So that is your Rosse number lah. So the greater the apa tu, kalau you tengok dia punya profile ni, so dia makin ke atas dia makin low. So the Z value is getting too low. So means that the concentrations dia dah tak jadi curvy dah, dia dah almost straight. They're almost straight. But if you look at down here, the velocity profile, or your Z value is getting higher, and then the concentrations of your profile dia jadi kecil, it's become small. Salah saya cakap ni. So kalau maksud dia kalau dia dekat dengan bed, okay, so dia punya Z value is high. Betul tak?
Betul.
Oh no, sorry. So bila dia dekat dengan surface, dia jadi apa ni?
Concentration is lower.
Lower. Kalau dia near the bed,
Higher.
it's supposed to be the other way around,
But the graph is put, surface is on top, right?
Yes. So kalau kita tengok graph yang tadi tu, our concentration is like this, right? So it's getting higher down to the bottom. So that is what explained by this graph lah. Okay. So apa yang you tengok dekat sini is that on your y-axis, on your y-axis is the value of your y minus a divided by d minus a. So a here is this thickness of your bed layer. So a ni sebenarnya dia ada banyak juga cara dia nak determine. So Einstein say that the thickness of the bed layer is equals to the 2 minus d90. So ada banyak approach lah, but normally the thickness of the bed layer ni will be given to you lah. For example, in this diagram, Rose determined that the thickness of the bed layer is equals to the 0.05 multiplied by the depth of your water, of your water depth. Okay. So C here is the concentrations at any profile, at any depth. Okay. And then CA here is the concentrations at bed loop layer thickness lah. So kalau you ada profile macam ni, and then you have take one of 0.05 multiplied by D, which is your bed layer. So your concentration will become like this, and then this concentration A is at this point. Okay, the concentration C is along this curve. Along this curve. So this is the Rose profile, the original Rose diagram or Rose profile kita panggil. And then in case if your beta is lesser than 1, so you boleh pakai this Ching diagram to determine what is the value of your Z1. So this is the line of your Rose where Z is equal to Z1. And then this is the line where your beta is lesser than 1, then your Z is greater than Z1 lah. So you kena cari dulu what is the value of Z, hit this line, and then you will get what is the Z1. Okay, so yang tadi tu what we have discussed is that we want to know the concentrations, the sediment concentration, C, and also the CA. Okay, kita belum lagi calculate the sediment transport, which is our QS. Ni belum lagi calculate. So, but because we know that the QS earlier is equals to the integration from D to A, U times the C. C is the sediment concentration. So you can use the Rose diagram, so Rose equation, to calculate what would be the value of the sediment concentration. Okay. Now barulah kita calculate what is the value of the suspended sediment transport. So the first equations that related to the suspended load transport is given by the Linz and Kalinsky in 1941. Okay, so kalau you tengok this equation, it is equals to this Q, the sediment discharge per unit weight, multiplied by the CA. So the CA is the concentration by or the concentrations of the sediment at A, at a bed load thickness layer, and then multiply by the PL, exponentials distance. So PL ni adalah factor in a functions of this shear velocity and also this flow depth, the roughness over the flow depth. Okay, so kita boleh use, we can use this diagram to determine what is the value of PL. The CA ni kita boleh determine from the rows equations. Okay, but the PL, you can use this diagram. Okay, so on your x-axis is your relative velocity. So you kena dapatkan you punya fall velocity using this Stokes theory yang you dah belajar waktu week 2, and also you have to find what is your shear velocity lah, which is equals to your tau load over E, right? So once you calculate that one, you also must know what is the roughness, your roughness M, and also your particle size D. Sorry, your flow depth, not particle size, your flow depth D. Okay, don't confuse with small d and big D. Yeah? So kadang-kadang ada pakai big D, kadang-kadang ada pakai small d, and then you have to know lah whether it is a sediment size ataupun it is a water depth. But for the Kalinsky, a big D here is your flow depth. So in order to use this diagram, your flow depth D must be in a unit of a British unit lah. So in inch, not in millimeter. Okay. So once you get these two parameters, you hit one of the line, and then you will get what is the coefficients of the P over, what is the coefficients of the PL. Okay, so W here is your fall velocity. A here is the thickness of your bed layer. The thickness of your bed layer. Right. So D here is your depth, water depth.
Doctor, the D in the equation has to be in inches also, is it?
Sorry?
In the equation there's a D there. That is in inches or in meter?
L.
Written there, doctor, in
It's
inches.
inches, yeah. It's inch, Manoj, yeah? Okay, so the second transport formula is by Brooke, 1963. So kalau Brooke sini pula dia calculate the sediment concentration at the mid of the depth. So dia nak cari concentration sebab dia pakai concentration at the mid depth. Dia pakai C mid here. CMD ni adalah concentration at the mid depth lah. So you have to, your Y is equals to D over 2 lah, at the mid depth. And he said that is a functions, TB is a transport function. Ini tak ada apa-apa terms. So it's a transport functions as a functions of these terms and also these terms, the Q and also the Z1. Okay, so what we want to find here in this equation is this QSW. And QSW, or the suspended load transport rate by unit weight. Okay, by unit weight. So per meter, right? So Z1 is the one that you can determine from the Chen's graph. But in this case, then your beta should be greater, or sorry, should be lesser than 1 lah. Should be lesser than 1, and it will be given to you. So similar also to the Kalinski. So Baruch also comes out with this graph between this Z1 and also these transport functions or sediment transport. So dalam equations ni kita nak cari what is this QSW. Okay, so QSW divided by the Q times the C mid, C concentration. So these lines represent this transport parameter lah, K times V over shear velocity. Okay, so dia dah bagi this value, so you just need to determine what is your Z1. Okay, hit one of the line and then go straight to the left, then you will get the parameter for this sediment transport, and from there you can determine what is your QSW. QSW. K here is the von Karman constant, the von Karman constant, which is always equals to 0.4. So maksudnya in order to solve these equations, then you have to use this graph. You have to use this graph. Okay, the next one is Chang, Simon, and Richardson equation, which is given by this expression. So this is the unit weight of water, and then D here is your depth, water depth. Ca is the concentration at the bed level or bed layer. V here is your velocity. Ini bukan kinematic viscosity. So V here is your velocity or average velocity, and multiplied by the I1. So I1 ni dia adalah transport functions also. And also I2, also a transport function, which you need to use the graph to determine these transport functions. And then you have this U star is your shear velocity, and then you have this K is your von Karman constant, which is 0.4. So the I2 and I1 and I2, the transport function, is determined based on these terms, two terms, eta A and also this Z2, okay, which is given by these equations. Okay, macam mana you nak determine the value of this eta A, then you use these equations, A divided by the D. So A here is your bed load layer thickness. Bed load layer thickness. Kalau you pakai rules ID, it is equals to 0.05 D. D is your water depth. And then Z 2 here is equals to this forward velocity divided by this beta times the shear velocity times the von Karman. So here is the graph for the transport functions of I1, which is on your y-axis, I1, and then your x-axis is your eta A. So the eta A is this backload transport punya thickness lah. So you dapatkan eta A from the previous equations, and then here is the lines of your Z2, starting from 0.1 to 10. Okay, and then you hit one of this line based on the Z2, calculate from the previous equation, then you can determine this I1. You can determine this I1. Similarly also for the I2, so you dapat the I2, you can determine the I2 from your y-axis and the eta A. Eta A on your x-axis, and then the curves in the graph give you the value of the Z2 from the 0.1 until 10. Okay, so kalau you interested, you can study on kenapa dia punya graph ni jadi macam ni untuk transport function of I2 and also the I1. So cantik dia punya graph ni. Cantik dia punya graph ni. So Z also is depending on the forward velocity lah. So you kalau ada different forward velocity.
Doktor,
Yeah.
can we take 5?
What is time now?
2 minutes.
Oh, we should stop. We don't take 5. We should stop. Okay, so maksudnya macam tu lah. Right. So that is the end of this suspended load transport. So cuba nanti buat untuk this example similar to the backload transport tu juga. Kalau you have to look at into the equation first. Kalau equation to suspended ni kita ada 3 sajalah, tak banyak. But you have to refer to the graph to determine some of the transport parameter. Okey. Aduh. Dah pukul 12 rupanya. Tak perasan saya. Mana muka saya? Oh, okey. Dah lupa, we have to stop here to give times for Abby, Asina, Manos, and also Kavi to prepare for this to prepare for the IPA Bali tomorrow.